viewers, in this session I would like to focus my attention to spatial analysis methods that can be implemented on a GIS database. Before we start the analysis in GIS, it is important that we observe certain rules. Before starting any analysis, one needs to assess the problem and establish an objective. It is important to think through the processes before making any judgments about the data or reaching any decisions. Ask the questions about the data and model and generate a step-by-step procedure to monitor the development and outline the overall objective. The following steps outline the basic procedure for geographical analysis. First, establish the objectives and criteria for the analysis, that is, define the problem and then identify a sequence of operations to produce meaningful results. Second, prepare all map coverages for the proposed data analysis and add one or more attributes to the coverages in the database if necessary. Perform the spatial operations and combine the coverages, that is, creating buffer zones around features, manipulating spatial features and performing polygon overlay. Prepare the derived data for tabular analysis and make sure that the featured attribute table contains all the items needed to hold the new values to be created. Perform the tabular analysis, that is calculation, and query the rational database using the model defined in step 1. Evaluate and interpret the results and determine whether the answers are valid. Simple map displays and reports can help in this evaluation. Redefine the analysis if needed and repeat the analysis if required. Data analysis in most GIS packages, including measurement techniques, query on attributes, on proximity analysis, overlay operations and analysis of models for surfaces and networks. Let us first of all look at some of the data analysis terminologies before we proceed ahead. First is entity. An individual point, line or area in a GIS database is called an entity. Attributes. Attributes are characteristics of an entity. In vector GIS, attributes such as name of a road, average rainfall in an area are stored in a database. In raster GIS, an attribute of the value of a cell in the raster grid form in the form of a numerical code such as 1 for metalled roads, 2 for unmetalled roads, etc. Feature. A feature is an object in the real world to be encoded in a GIS database. Data layer. A data layer is a data set for the area of interest in a GIS, normally containing data of only one entity point, that is points, lines or areas. Image. A data layer in a raster GIS is called an image. Cell. An individual pixel in a raster is a cell. Function. Function or operation is a data analysis procedure or operation performed by a GIS. Algorithm. A sequence of actions to be performed by computer to solve a problem is known as an algorithm. So, now let us look at some of the basic tasks which may have to be done during the analysis procedure. First is measurement of length, perimeter and area. Measurement of length, perimeter and area is a common task in GIS. It is important to note that all measurements from a GIS will be an approximate due to the reason that vector data that are made up of straight line segments and all raster entities are approximated using a grid cell representation. If we are to make the measurements in a raster GIS, the Euclidean distance or the shortest path between 2 points A and B can be measured by any one of the methods given below. First is by drawing a straight line between A and B and computing its length as hypotenuse of a right angled triangle ABC by Pythagorean theorem, that is AB is equal to under root of AC square plus CB square. So, if the cell sizes are of unit length, then as per this particular figure as shown here, the distance of AB would be 5.7 units. The second technique could be measuring distances along the raster cell sides as shown in the figure, that is along the path AA, AB, BC, so on to GB and adding them up. That is AB is equal to A small a plus small a b and so on, and what we find is that by adding, since these sides are all of unit length. So, the distance of the between the 2 points A and B is of 8 units. Another technique is by forming concentric equidistant zones around the starting point A, and thus AB can now have a distance which is equal to 5.7 units as determined in the first method. Measurement of perimeter. In the raster GIS, the area and perimeter measurements are affected by location of origin and orientation of the raster grid, and these problems are solved by proper selection of grids with north south alignment and use of consistent origins. Measurement of length, perimeter and area in vector GIS is easier and accurate compared to raster GIS. The length of the line AB is calculated as below, where AB is equal to x b minus x a whole square plus y b minus y a whole square, taking the square root of these, where x a, x y a, x b, y b are the coordinates of point A and B respectively. In order to make measurement of an area, the area of a feature is calculated by totaling the areas of simple geometric figures formed by subdividing the feature or directly applying the following formula. So, using the polygon which has been shown in the figure, the area of the polygon A, B, C, D, E, A can be expressed as half within brackets A x A multiplied by the difference of y b minus y e plus x b, that is the difference multiplied by the difference between y c minus y a plus x c multiplied by the difference between y d minus y b plus x d multiplied by the difference of y e minus y c plus x e multiplied by the difference between y a minus y d. The perimeter is determined by summing up the lengths of all the sides. The calculated length perimeter and area can be stored permanently in a vector GIS database as attributes, and to use them needed, thus avoiding repetitive calculations. The next type of analysis in GIS is through queries. Performing queries on the database is an essential part on GIS. Some queries may require the data that is the result of data analysis. Generally, the query can be in the form, that is, what is the shortest distance between 2 points, or what is the route that will take minimum time to travel between 2 points, or what is the total area covered by a forest, or how many police stations are within a distance of 500 meters from a particular point, or it could be what is the distance of the nearest hotel from a particular point, maybe an airport or a railway station. Queries help in GIS analysis for checking the quality of data and the results obtained. The queries may be defined as spatial queries or aspatial queries. The queries which require spatial analysis fall under the class of spatial query, while aspatial queries use only attribute data of features involving no spatial analysis. A query such as how many hospitals with heart care facilities are located in a given area is a aspatial query, as it can be performed by the database software alone and does not involve the analysis of spatial components of the data. It is possible to combine the individual queries to identify the entities in a database to satisfy 2 or more spatial and aspatial criteria. For example, where are the hospitals which have more than 10 private wards? In order to do this sort of analysis, Boolean operators such as and, not, or nor are often used to combine different data sets by overlaying. Another form of spatial analysis in GIS is reclassification. Reclassification is another form of query in raster GIS, with only difference that it results in a new image in which the features of different classes have different codes. If the cell value of a particular class of feature selected is say 10, then in the reclassification all the cell values with value 10 may be assigned a new value say 1, and the remaining cells with various classes of features may be assigned a value 0. This will result in a new image which only highlights a particular selected feature. This new image is a Boolean type of image. It is also possible to create a new image by reclassifying the features, assigning new cell values that indicate weightage of different classes, and the weightages may be based upon certain criteria. This particular slide shows a raster map wherein 5 different categories of land use have been identified and have been given different codes. For example, wetland has a code of 8, water has a code of 9, agriculture is coded as 10, forest as 11, and industrial area as 12. Now, from this particular raster data, the analyst is interested in only finding out those areas which belong to agriculture. So, in the reclassification procedure, he will now assign that all those cells which have a value of 10 should be assigned a value of 1, while any other code or numerical value should be assigned as 0. So, this will lead to the formation of a new image having new cell values of 0 and 1 only, which is very similar to a binary image, wherein one may have a concept of 0 or 1, which is a 1 bit binary data. A analogy very similar to an electrical switch, that is 0 is equal to no current and 1 is equal to full current being supplied. So, here what we are doing here is that we are extracting only the agricultural information by highlighting it and masking all other information. Another form of GIS spatial based analysis could be through buffering and neighborhood functions. Buffering function, also known as proximity function in GIS, is one of the neighborhood functions and is used to create a zone of interest around an entity or sets of entities. Buffering allows a spatial entity to influence its neighbors or the neighbors to influence the character of a entity. Another neighborhood function that includes data filtering involves the recalculation of cells in a raster image based on characteristics of the neighbor. If a point is buffered, a circular zone is created and buffering lines and areas create new areas, as it can be seen in the next set of figures. Buffering could be about a point wherein the analyst may identify a certain area of interest about a particular point, or he may identify a strip wherein two different distances may be identified and the influence between the same could be there. For example, an analyst could say identify the region that a police station can cover within, or the houses which can be covered by a police station which is at a 50-meter interval. All right. The second case could be that the query could be made through buffering, wherein it could be made that a particular entity to be analyzed should have a certain minimum distance, but it should not exceed beyond a maximum distance. That is, the region could be split into two concentric rings of different radiuses. The same technique could be applied for a line, wherein one can have a distance identified, that is, from a particular line a specified distance can be given, that is, that along a particular sewer line, houses which are 40 meters on either side would be allowed to drain their sewer into their main sewer trunk line. Similarly, the buffering action can be carried out over an area in order to identify again influence zone. In this particular case, the area could be irregular in nature, as it may have been seen that in point buffering the area under influence is a circle, but in this case it could be a irregular polygon. Another important neighborhood functioning is point pattern analysis. Historically, point pattern analysis was first noted in the works of botanists and ecologists in the 1930s. Point pattern analysis involves the ability to describe patterns of locations of point events and test whether there is a significant occurrence of clustering of points in a particular area. In general, point pattern analysis can be used to describe any type of incident data. For instance, we may want to conduct hotspot analysis in order to understand location of crimes, or else we may want to study breakouts of certain diseases to better see whether there is a pattern. In both these cases, point pattern analysis can be of great help to institutions and policy makers in their decision on how to best allocate their scarce resources to different areas. In order to perform point pattern analysis, there needs to be some criteria, and the data must meet these 5 important criteria as indicated below. First, the pattern must be mapped on a plane, meaning that you must need both latitude and longitude coordinates. A study area must be selected and determined prior to the analysis. Third, the point data should not be a selected sample, but rather the entire set of data you seek to analyze. The fourth criterion is that there should be one-to-one correspondence between objects in the study area and events in the pattern. Finally, the points must be true incidents with real spatial coordinates. For example, using the centroids of a census tract would not be a especially useful process. So, let us look at what are the techniques by which point pattern analysis can be carried out. These could be done with the help of quadrant count methods, kernel density estimates, sometimes called as k-means, and nearest neighborhood distance. So, let us look at quadrant count methods. This method involves simply recording and counting the number of events that occur in each quadrant. In general, it is important to remember that larger quadrants produce a very coarse description of the pattern, but as quadrant size is reduced, many areas may become too small and some may contain no events at all. In order to do the computations, we will use the thumb rule for the area of a square is twice the expected frequency of points in a random distribution, that is 2 multiplied by the area divided by n, where n is the number of points in the sample size. After partitioning the data set into quadrants, the frequency distribution of the number of points per quadrant has to be constructed. The mean and variance of the sample are then computed and computed to calculate the variance to mean ratio, or in short VTMR. So, how do we now proceed with the interpretation? So, we will now interpret the VTMR of a sample as follows. The first criteria is, if VTMR is greater than 1, it may be concluded that the pattern is clustered. This implies that the data set has one or more groups of points in the clusters and large areas of maps without points. This region might look as shown in the adjoining figure, wherein we find that the points are appearing in small groups where and in between the groups there are no information or no points are lying. This is what we call it as a clustered pattern. The second condition is that if VTMR is less than 1, the pattern is regularly dispersed, implying the events are distributed more or less regularly over the region. A regularly dispersed area might look at shown in the adjoining figure, wherein we find that points are distributed over the whole region and there are no concentration of points at any region within the sample space. The third condition is VTMR is equal to 1, that is the pattern is random. This implies that the data set has no dominant trend towards clustering or dispersion. A random pattern may look like as shown in this particular figure. Here one may see that there are some regions where there is a concentration of points, whereas in some region there is a sparse layout of points which is there, that is the density is low. So, one may not be able to give any concrete conclusions regarding the distribution of the points which is there, and thus this is a random condition which is existing. The next point pattern analysis technique is through kernel density estimation. This method counts the incidents in an area within a kernel centered at the location where the estimate is to be made. This analysis is a partitioning technique, meaning that the incidents are partitioned into number of different clusters. Often the user is able to specify the number of clusters. In some form of this analysis, all incidents, even the outliers, are assigned to one and only one group. Well, when we look at this particular method, there are some advantages which are there. It is very good for analyzing the point patterns to discover hot points, provides with a useful link to geographical data, because it is able to transform the data into a density surface. The choice of R, that is the kernel bandwidth, strongly affects the density surface. Further, we can weight different patterns with other data such as density of population and unemployment rates. The next type of neighborhood analysis is nearest neighborhood analysis. Nearest neighborhood analysis examines the distances between each point and the closest point to it. The nearest neighbor is a method of exploring patterns in a locational data by comparing graphically the observed distribution functions of event to event or random point to event nearest neighbor distances, either with each other or with those that may be theoretically expected from various hypothesized models, in particular that of spatial randomness, that is, it describes the distribution of points according to their spacings. The nearest neighborhood analysis can be expressed by a index known as nearest neighborhood index. The nearest neighborhood index measures the degree of spatial dispersion in the distribution based on the minimum of the interfeature distances, that is, it is based on the distance between adjacent point features, such that the distance between the point feature in a clustered pattern will be smaller than in a scattered uniform distribution with random falling between the two. The equation for the nearest neighborhood is computed through the following steps. Step 1. Compute the average of the nearest neighbor of the point pattern using the equation AD is equal to summation of DI divided by N, where DI is the distance of point I to its nearest neighbor, N is the total number of points in the chosen map area. Step 2. Compute the expected value of the average nearest distance ED, which is equal to half under root of A divided by N, where A denotes the map area and L is the total number of points within the map. Now, compute the nearest neighborhood index, in short NNI, which is defined as the ratio of AD to ED. The values of NNI range between two theoretical extremes, that is 0 and 2.1491. When all the points in a pattern fall at the same location, the pattern represents the theoretical extreme of spatial concentration. In this case, AD is equal to 0 and NNI is also equal to 0. The more closely the points are clustered together, the closer to 0 NNI will be, since the average nearest neighbor distance decreases. The closer NNI gets to 1, the more randomly spaced the points are. The value of NNI approaches 2.1491 for a perfectly uniformly spaced points. Hence, the closer NNI is to the value of 2.1491, the more uniformly spaced the data are. Well, in this slide, for certain typical values of NNI, the distribution of points have been depicted. For NNI equal to 0, we find that the points are lying very close to each other, and this is what we call it as a cluster of points. When the value of NNI is equal to 1, we find that the same set of points now tend to get spread out over the data space, but do not exhibit any form of regular pattern. This is what we call it as random. So, when NNI is equal to 1, the distribution of the points is random, that is, no structured form of data collection has been adopted while collecting the data from the ground. However, when this value of NNI is equal to 2.15, the viewer may see that now the points are distributed within the feature space in a very regular, orderly, structured manner, and this is what we call it as regular distribution of sample points. The next method of spatial analysis is filtering. Filtering is one of the functions of neighborhood used for processing remote sensing data. Filtering changes the value of a cell, which depends on the attributes of the cell in the neighborhood. A filter comprising of a group of cells around a target cell and its size and shape are decided by the operator. A filter may be square or circular in shape, and its size determines the number of neighboring cells used in the filtering process. The filtering process involves passing of a filter of predetermined size and shape across the raster data set to recalculate the values of the target lying at the center of the filter. The next figure shows a square filter which has been applied to recalculate the value of the cell CD, which has a value of 4. So, what we find is that a filter of a particular slice is now placed over the target pixel, and corresponding to this particular configuration of the filter, a new value would now be calculated. The recalculated value of the target cell DC depends upon the criterion used in the table. The filtering may be required in the raster data obtained from a classified satellite image to smoothen the noise present in the data due to high spatial variability in a particular class of feature such as vegetation cover, or due to problems with the data collection devices. So, when we apply different criterias, well, these criterias in GIS we call them as filters. So, when I apply a minimum filter to the target cell DC, which is having a 3 by 3 window, the new value which that would be assigned to the target cell would be 1, because the minimum value amongst the 8 neighborhood around the target pixel or cell is 1. If I apply the maximum filter, then about the 8 neighborhood points about the target pixel, the maximum value is 4. I can apply a mean filter, that is, it will calculate the mean of all the 8 cells which surround the target cell and find out what is the mean value and replace it by the same. So, in this example, the mean value comes out to be 2.67. So, the new value for the target pixel is now going to be 2.67, and interestingly, one may find that this is not a value which any of the neighborhood pixels of the target pixel have. So, what has happened is a new value has been computed. It is very important that for these type of filters, the analyst must bear in mind that what should be the structure of storing the output value, as has been indicated earlier, because if the file structure only allows for integer values to be stored, then this particular value will not be stored. Either the GIS package will show that there is some error in the output stage, or it will undertake a process of rounding off. The rounding off can be as per the normal condition, that is, it could now be assigned to a value of 2, or if one provides a criteria that it should be to the nearest integer, then the value instead of 2.67 it would be stored as 3. So, these are some of the considerations which the analyst must keep in mind for different types of operations which he may have to perform. The next type of criteria could be a mode filter. A mode filter is nothing but it finds out the values of the 4 of the 8 neighborhoods, and what we find is that the value which is most common about this particular cell is the value of 4, and thus the value is given as 4. Okay. The next criteria could be a diversity filter. Again, on the basis of the information which is there, the new value could be now assigned as 4. Another type of information of spatial analysis could be texture transformations. Texture transformations are another set of tools that are used to identify the spatial pattern in data. Texture filters are designed to enhance the heterogeneity of an area. A common algorithm of a texture filter is to calculate the standard deviation of the cell values in a 3 by 3 neighborhood. If the attribute values in this neighborhood are all similar, the standard deviation is small, and it is said that this neighborhood has low texture or low variability, and in case there are many different attributes in a neighborhood, we will have high texture. Texture filters are also used to find out the boundaries between delimited areas, since texture of a homogeneous area must be equal to 0. Another type of neighborhood analysis is slope transformation. A slope transformation turns a data layer of elevation into one of slope by calculating the local first derivative. A companion to slope is aspect. An aspect calculation is used to determine the direction that a slope faces. A mathematical way of explaining aspect is to calculate the horizontal component of the vector perpendicular to the surface. Aspect is usually classified into bins of fixed sizes, so that the resulting data layer is not continuous, but ordinal. A frequent choice is to classify slope into 8 categories representing an eighth of a circle or 45 degrees range in aspect. Other neighborhood functions. The characteristics of data set along a specific line can also be determined by the use of another neighborhood function. Such a process is commonly presented in the form of graphs or profiles or cross sections of the data set. Profiles are used to determine the slope along a line between 2 points for the construction of a highway or a canal, or to determine the intervisibility between 2 points. In my next session, I will discuss the other methods of spatial analysis, that is map overlaying, spatial autocorrelation and network analysis. Thank you.